So let's discuss one of the important version of the substitution rule. In some books you can find these formulas, but I hardly see them in our textbooks, or like even the textbook that we use last semester. So let's talk about these ideas in a kind of short way. So what I'm going to call these four formulas. So we're going to call it four formulas. Okay, four formulas. So what are the four formulas? So let's try them first, and then and we are not going to prove any of them, but I'm going to show you how to do it. This is just a substitution rule, substitution method, but these formulas are very useful in the future and also in some other courses, because this can make the most of the integral calculations much faster. So let's go one by one. So I'm going to call the first one number 1. So this is what we normally call a generalized power rule. So what is the generalized power rule? So if you have an integral of fx to the nth power, and also you're going to see the f prime x derivative, so derivative of the inside function dx. So if this is the case, you can simply treat fx as x, because if you know that if we have x, it is x to the n, the integral is x to the n plus 1 over n plus 1. That's the integral. So we can use very similar idea here. You can simply treat fx as x. So if you consider fx as x, you're simply gonna get fx to the n plus 1 power divided by n plus 1 plus c. So this is what we call a generalized power rule. That's the first formula. So this formula works if n not equal to -1. That's the formula number 1. Formula number 2. So you can have a similar result. Like what if you have e to the fx dx, e to the fx f prime x dx, like that. So let's think of the corresponding formula in exponential function. We know that if you have exponential function e to the x, the integral of that is simply ex plus c. So the same idea. So if you see function along with its derivative, then you can simply treat fx as x. So that means you will get e to the fx plus c. That's the second formula. The third formula. So we have let's say you have a function, and then you have the derivative on top. Okay, like that. So this is like let's look at the corresponding formula with the regular function. If you have 1 over x, the integral of 1 over x is ln x plus c. You have the plus c there. So the same idea. So if you have fx and then its derivative on top, you're gonna get natural log fx plus c. And don't forget the absolute sign, because for the natural log to be defined, the argument has to be positive. Okay, so that we know. So but when you graph it like that, that means when you write the absolute sign, that means you consider both sides. So like that and like this. When you have absolute sign, it has both, otherwise it's only the positive side. But you can see that at 0 it doesn't exist. Okay, so when you take the absolute, you can consider the both sides. So you have a larger domain. So this is ln absolute value of x. So you have both sides. Okay, and then the fourth formula. So what's the fourth formula? So this is actually number 1, but for a special situation. For example, when you have ax plus b, because this is very common, to the nth power. So what's going to happen? You know that the derivative of the inside function is a, but a is just a number, so you can multiply and divide. And if you multiply and divide, what's going to happen? It's going to be so you can say that it is 1 over a. That's that multiply and divide, and then you have ax plus b to the n plus 1 over n plus 1 plus c. So these are the what I call four formulas. So make sure that you practice this, and then you can use them directly. So it's very easy to use, so you can save a lot of time. But so remember these as 4 formulas. Okay, when I say 4 formulas, this is what I mean. Okay, so remember these 4 as just one single set. So this can definitely help you a lot. And then here in the last one also, we assume that n not equal to -1. And then how to prove them? I'm not going to prove. So to prove them, to prove, just say u equal what? The inside function. Okay, just take u equal fx, and you can see that you can prove all of those formulas very easily. Okay, so but it's a good idea to remember this as a shortcut. Because this is very common in most of the other classes as well. So differential equations, also like in engineering and computer science, everywhere, physics. So we can use them. So if you remember this as like this, it will be much easier even to think, you know, what's really going on there. So I'm going to call these 4 formulas. Okay, 4 formulas. Okay, so just to practice it, let's do like a couple of examples, so that, like, you know, we kind of know how it works. So let's do a couple of examples. So how about the integral of, so let's say 12 x squared minus 12, and then you have square root 4x3 minus 6x squared plus 1 square root dx. Okay, so what you're gonna notice, you're gonna see what is the inside function and see whether it's a derivative there. So what's the inside function here? So that's the inside function, that is the fx function. Okay, that is fx. And what's the derivative? Derivative is that, so f prime x. So that means it's gonna work with formula number 1. So according to formula number 1, here n equal 1/2. So if you put n equal 1/2, you see fx and fx prime, so you can directly write the answer. So that means it's gonna be 4x3 minus 6x squared plus 1 to the is 1/2, so it's 3/2 divided by 3/2 plus c. Okay, so it's very simple, and just directly write it like that, because you're going to see fx and its derivative. Number 2. So a, and let's do another one. So how about this one? How about this one? Number b. So what's going to happen? So we have let's say t, and then t squared plus 1 square root dt. So how to do it? So what is the inside function here? Inside function is t squared plus 1, or fx equal t squared plus 1. What's the derivative? 2t. So number 2 is missing, but that's okay. What you can do, you can modify this as 1/2, and then we're going to put 2t, and then t squared. Actually, what we can do, we can write it like this. So it's easy if you write it like this. So we can write it 2t, and then t squared plus 1 negative 1/2. Okay, now you can see that we can still use equation number 1 again. Because you're going to see the function here, and then you see the derivative. So you can use the formula. So it is 1/2 according to the formula. So you're going to get t squared plus 1. You add 1, and then divided by the same number plus c. So that's the answer. Okay, and then if you simplify, you see 1/2 get cancelled. You're going to get t squared plus 1 square root plus c. And then let's do one more. How about this one? Number c. Let's say 3x squared plus 1 over x cubed plus x plus 5 dx. And if you look at the bottom function, and what's the derivative of that? It is 3x squared plus 1. That's exactly what you have out there. So that means according to equation number 3, this is simply ln x3 plus x plus 5 plus c, just equation number 3, okay, because the top is the derivative. Okay, so let's just do one last example. How about this one? This is useful in a later section. So let's say we have x to the squared plus 4 and then x plus 1 dx. Okay, now if you take the derivative, you can see that the derivative is 2x. Okay, but there's a plus 1 here. Since there's a plus 1, we can directly use this result. So what we can do, we're going to split this into 2. So I'm going to split this as x over x squared plus 4 dx plus, and then also 1 over x squared plus 4 dx. Okay, so for now, if you look at the first one, you can see that the derivative of the bottom is 2x. So what we can do is we can have 1/2 2x x squared plus 4 dx plus, I'm going to repeat this one, and then now we can write the answer directly. So what's going to happen, this is simply 1/2 natural log x squared plus, okay, and also yeah, well, let's write it x squared plus 4 plus, what is this? This is 1 over a squared x squared plus a squared. This is tan inverse. So here a equal 2. So that means it's 1/2 tan inverse x over 2 plus c. And I want to tell you one small thing, and you can see that in the natural log, this x squared plus 1 is always positive. So that means we can ignore this absolute sign, and we can simply write this one as 1/2 ln x squared plus 4 plus 1/2 tan inverse x over 2 plus c. So that's the kind of best answer if you can write, but there's nothing wrong if you write the previous one. Okay, so this is how we kind of do these kind of problems. Okay, so yeah. And then I also want to point out important and also will be useful. So what is this idea is, like, if you replace x with x plus a constant, the same formula works. And I'm going to say same formula works. And what does that mean? So actually one reason behind why this is going to work, and you know that if you pick u equal x plus k, if you pick u equal x plus k, what's going to happen if you take du, it is dx. So that means the derivative part, du part and dx part, they are the same. So that is one of the reason why the integral does not really change. So what does that mean is, let's look at some examples. So I'm trying to tell you, like, let's say a. So if you want to integrate, let's say 1 over x plus 3. So what this says that just consider the formula for 1 over x. Okay, consider the formula for 1 over x and simply replace the answer by x plus 3. So that means if you integrate 1 over x, what do you get? You get ln absolutely x plus c. So what are you going to do for this one? Simply replace x by x plus 3. So that means the answer is ln x plus 3 plus c. Okay, because it's very easy to show using the substitution rule, because you simply replace, you can simply gonna take u equal x plus k. Okay, so please remember this one, because this can also save a lot of time when you try to simplify certain things. So I'm going to do like 3 examples. Let's do one more. How about sine theta minus pi d theta? So you can see that the pi is a constant, so that means we can use the same idea. So simply treat this one as a regular theta function. So if you go sine theta, you're gonna get negative cosine theta. Okay, but what you can do in the answer, you're gonna replace theta by theta, theta minus pi. So that means a negative cosine, not theta, with theta minus pi. Okay, plus c. So that's the idea. So you can see, you can save a lot of time doing that. Okay. So it is e to the, how about this one, e to the t minus phi dt. Same idea. If you go with e to the t, it is e to the t, but it's not t, it's t minus phi, so it's e to the t minus phi plus c. Okay. Yep. So this is the end of what I'm gonna call the 4 formulas. Okay, and a simple trick. 4 formulas and a simple trick. Okay. So you are allowed to use this.